Hi, Matapelo here. Today we're going to be talking about the gas compressibility factor, which is the key parameter in ensuring proficiency and functionality in the industries such as refineries, petrochemical industries, gas plants, lastly oil and gas industries. Moving on. Depicted here is the generalized gas compressibility chart. It relates the reduced pressure and the gas compressibility factor of different gases. 10 gases are experimented on, and the results are depicted on the chart. Okay, so what is the reduced pressure? The reduced pressure is the ratio of the actual pressure to the critical pressure, and the reduced temperature is also the ratio of the actual temperature to the critical temperature. Critical temperature and critical pressure are the quantities that our gases need to have or need to reach in order for phase change to happen. Whereas the actual pressure is the pressure exerted on the walls of the container by the gas. In cases where our gas is unrestrained, we are going to experience the expansion of gas expanding to a lower pressure. And the temperature, the actual temperature, would be the temperature that the gas is in. On this very slide, we're going to be discussing the trends observed in the generalized gas compressibility factor. We can see that we have different lines that are connecting gases that follow sort of the same trend. So these gases, these lines, they are the TR lines. We're going to refer to them as the reduced isotherms because on these lines we experience our gases having the same reduced temperatures. So as we can see, the trend is such that as our gas compressibility factor approaches 1, the more linear our TR lines become, or our reduced isotherms become. What does then this mean? The more linear the reduced pressure is, the lesser the differences between the gas compressibility factors of the gases that have the same TR value. This means that as the lower your gas compressibility factor becomes, the larger the differences in the gas compressibility factors. Hence, the similarity is getting impaired. Moving on, we immerse in the example that puts on to practice what we've learned thus far and put more emphasis on it. Here is how it goes. 3.5 kilograms of propane in a rigid tank at 4,000 kilopascals, 110 degrees Celsius, is heated to 130 degrees Celsius. The first one, determine the initial volume in the tank in meters cubed using data from the compressibility chart. So the fact that we have to use data from the compressibility chart, it means we are going to read something. And as you look at your equation for calculating the gas compressibility factor, you have the specific volume. And the specific volume can help you to find the volume. Hence, we need to find values that are going to help us to read the gas compressibility factor from the chart. We start by calculating the reduced temperature and the reduced pressure by making use of the critical temperature and the critical pressure is read from the thermodynamic table. From there, we read our gas compressibility factor to be 0.52. Going on from there, we substitute it in our equation for calculating the gas compressibility factor, and we find our specific volume as that. We further on substitute it into our equation. Volume of a substance equals to the mass of the substance times the specific volume of the substance, and we find our volume to be that. So basically, this is how you make use of the gas compressibility chart. You ensure that you have your reduced temperature and your reduced pressure to help you read your gas compressibility factor if you don't have enough parameters to be able to calculate the gas compressibility factor. Moving on. I begin to